Hello fellow problem solvers. So today we're going to be doing a problem from the 2015 Romania Junior Balkan Math Olympiad Team Selection Test, Day 2, Problem 3. I suggest you try this problem out for a minimum of 20 minutes, ideally an hour, but not more than an hour and a half. If, on the other hand, you'd like to go along with us, I suggest you take 10 to 15 minutes and try to play around with the problem. So now, let's begin. So this is what the problem is asking. Can we partition the natural numbers into two sets, A and B, such that for any arithmetic progression that has a non-zero difference, one of the members is in A and the other one is in B. So how do you even begin trying to answer this question? Well, let's think about this. The question is it possible or not? And one way to figure out, if we're going to try to prove that this is impossible, we might as well try to look for constructions and see what sort of things become problems. But also, basically, let's look at some general things. So if these k and l exist, then there do exist also consecutive, there exists a k such that a plus dk is an a, and a plus dk plus 1 is in b. There exists stuff like this. Now we can also ask, what does it mean for this to be a arithmetic progression? Well, this is just a set of numbers that are congruent to a modulo d, and that start from a. And it's all numbers starting from a that are congruent to a modulo d. So in other words, if such an a and b exist, this means that both a and b have, for every d that's an integer, A and D have infinitely many elements which are congruent to 1 mod D, 2 modulo D, all the way till D minus 1 and D modulo D for every single D. So this is a thing that needs to hold for both A and B. So now that we've explored this problem together till this point, I invite you to take another 10 to 20 minutes and see if you can push the problem further. So the question is, how could you fulfill this easily? Well, the idea is, okay, let me give d of them to A and then d of them to B, and then continue giving them d and d, d and d. Now the problem with that sort of thing, for a fixed d, this is great, we can actually do this. We just give, say, for d equals 2, 1, 2 to A, then 3, 4 to B, then 5, 6 to A, then 7, 8 to B. But the trouble is, if we continue just doing this for 2, we will miss 4. All of these are 4k plus 1, all of these are 4k plus 3 and 4. Now the next thing to notice is, if we have d of them, we also have d minus 1 consecutive ones, and we have d minus 2 consecutive ones, which means we have all the remainders till d. So now, from here, you can maybe get an idea of a possible construction. With this in mind, I invite you actually to try for 5 to 10 minutes to construct A and B. So there are many constructions, but mine was, I give A 2, I give B 3, then I give 4 and 5 here, 6 and 7 here, then I give 4 here, I give 8, 9, 10, 11, 12, 13, 14, 15, So what I'm doing is, because I have two things, I just wanted to make it look nice. And if I transform them into base 2, I'm giving 1, 0 to A, 1, 1 to B, and then 1, 0, 0, and 1, 0, 1 to A, 1, 1, 0, 1, 1, 1 to B, and then 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, actually 1, 0, 1, 0, 1, 1, 1, 1, 0, 1, 1, to A. And as you can see, I'm making A the set of numbers which have a 0 in their second to last position when written in binary or just second position. And I just thought that was cute, nice. And the thing is, both of these will have, you can just say I give 1 to each, and I give 2 to, I give the next 2 to A, then 2 to B, 4 to A, 4 to B, and so on and so forth. And the reason this thing holds true is because for any remainder in any D, we will have d consecutive integers in A and d consecutive integers in B. And now, 1 doesn't matter. We can just give B everything else, including 1. And this completes the problem. This means that it is possible to partition the set of positive integers into two sets such that neither contains an infinite arithmetic progression. You can write up the proof yourself, and this concludes our problem. And as always, thanks for problem solving.